afternoon, everyone. We are going to start today's session. So today we'll start with the Kaplan-Meier product limit estimation method for survival analysis. And then we'll go to the breakout room and we'll learn these two processes on SPSS as well as in JAMOVI. There were a few questions regarding the SPSS, regarding the probability density, and the other one was regarding the why that number on JAMOVI, it was exceeding that number at risk. So we'll explain both these two concepts before we go to the breakout room. Before that, we'll start with this Kaplan-Meier product limit estimation method of survival analysis. So on day one, we discussed that there are three ways of doing this. There are many ways rather, but in this workshop, we'll focus basically on three methods. The first one is the life table analysis, which we learned on day one. The second is the Kaplan-Meier product limit estimation method, where we compare more than one curve using a log rank test, or there are various tests. And then third one is the Cox proportional hazard method. So if you see this Kaplan-Meier, so now you know what is the importance of censoring of the data, and how do we calculate for the censoring, what is a survival and what is a cumulative survival. So one thing is to remember that this survival probability, this is a instantaneous survival probability, and the cumulative of survival probability at one point of time is often multiplicative of the previous one. So we can say that we'll see that it's not the additive. So you have to remember that. So now this estimation of survival probability, we always call it as a conditional probability, because I'm not going into the mathematical concept involved, because in survival, if you see a lot of mathematical jargon and mathematical formula that works in the background, because it's entirely a mathematical concept. That's why we have kept those mathematical concepts up to a very minimal level, and we'll focus mostly on how to perform this, and once that result has come up, how to write and how to interpret that. So like I was saying that this Kaplan-Meier, it is a product limit estimation method, and the survival probability at time t. So this is because we always say that event as a failure. So in day one, we discussed that whenever that event will happen, that is known as the failure, and person who survived that event, in whom that event has not happened, after that, they are known as the survivor. So past to a certain time, if the person has survived beyond that time, we call it as a survivor. So this, you can see here that the survival, that is a function at time t. So survival probability at time t, it is the multiplicative. So it is the multiplication of P1, P2, P3 and Pt. So P1 is the probability of subject surviving at least 1 month, or maybe whatever is the time, because there are different time points. So at least whenever that first event happened after beginning of the study, this P2 is the conditional probability of surviving the second month after having survived in the first month, and then T, which is the conditional probability of surviving in the Tth month after survived in the T-1 month. So this Kaplan-Meier analysis, when you see this, either we always say that there is an event or there is no event. So when there is no event or no failure, we call that as a censor or the censored data. And because of that, we have seen that we need to perform the survival analysis, because if we could follow each and every person up till the development of the outcome, we don't need to have a survival analysis. In that case, you can directly go to maybe the person time calculation, that is the incident rate, or you can simply calculate the incidence. But because of these censored data, because you have followed a person, and because of some reason, and mostly because we were discussing the type of censoring also. So in survival analysis, mostly it's the right censoring which happens. The right censoring will be like if there is a dropout, or if the person withdraws from the study, or if there is a loss to follow up and you don't know about the outcome, you are not sure what was the outcome. So because of that censor, then that censoring of the data, that is quite a lot in proportion. Like if you see that it is approximately 20 to 30% of the total sample which you take in a, whether it is a randomized control trial or it is a prospective cohort study. So either you measure the overall time to event, when you can have a graph like this, you will have a single graph, or you can compare time to event across an independent variable. Like in this case, you can see we are comparing the cumulative survival and against the gender, that is the male and female. So this can also refer to the proportion, the survival, it refers to the proportion who are free of for another outcome event, that is the percentage in this case, because in the last class also we saw that the development of the second MI. So the percentage free of MI or cardiovascular disease, or it can also represent the percentage who do not experience a healthy outcome. So now whenever you compare two survival curve, the choice of the test is basically the Kaplan-Meier. And we plot the different survival curve. In what situation you can plot? So if there is a randomized control trial, you can plot this survival curve across the different arms in a clinical study. You can again plot this curve across any hypertension, any risk factor, like maybe hypertension present or absent, cardiovascular disease present or absent, or across the various categories of BMI, if there is a lipid profile, hyperlipidemia versus normal lipid, or across gender, maybe if that is an inherent risk factor for a disease. So generally we plot the survival across the survival curve across a risk factor, because that gives you the estimate and the median survival time. So in studies involving comparison of two treatment, we only need three information. So we need, there is a treatment group, we need follow-up duration. Like in this case, you can see we have followed the first person up till 120 days. And in this case, the event has occurred. Second case, we have followed this person B up till 400 days and the event has not occurred. In the third case, we have followed this person up till 250 days. And in this case, the event has not happened. In the fourth individual, you can see again the event has happened. So in this case, you can see that 1 and 0. 1 is for the event happened and 0 is for the censored cases. So now there are various options which you have in SPSS and probably in, I think JAMOVI, it gives the log rank most commonly. It subjectively compare the curve to look for any difference in the survival probability. So that log rank, there are log rank, you know, there is a Breslau also, which is also known as the Wilcoxon test, and there is a Taron-Ware test. So if you see this log rank, generally, if you want to see the early part of the curve, generally we use the Wilcoxon or the Breslau test. If you want to see the later part of the curve, generally it's the log rank test, which is used, and Taron-Ware can be used in the middle of these two. So like in this case, there's a person, there's a group like treatment A, this subjects are the heart attack and the patient is receiving treatment A. And if you want to know what is the estimated probability following the first heart attack that he will survive more than 3 years. So to answer such questions, you need survival data or the survival analysis. So now what is a median survival time? And why do we calculate median survival? Why not mean survival? So we'll ask this question once we will show you the analysis and then we can ask the question. So Dr. Shibaji is asking how we decide the cutoff for the early, middle or late. So actually this is not the cutoff in the graph. If you can hypothetically divide the graph into 3 parts, then maybe that first 1/3 will be the early, middle 1/3 will be the middle, and the later 1/3 will be the late. That's usually, there's no such cutoff which we describe if we have to choose a test like that. And there should be a reason which we should be defining earlier. So it all depends on the research question. Like if I want to see an effect of a drug on the control of hypertension. So from the previous research, I know that the effect should have come up till maybe the first 2 months. Then in that case, I will look up on the Breslau test or the we can say Wilcoxon test. But if I know that the effect of a particular drug, it is going to be like late, maybe 9 months, maybe 1 year. So in your study period also, because you have calculated, you have decided for a study period. So like if you are planning a study for 5 years, so then you can say that the later part, if you are anticipating the response of a particular drug in the later part, maybe the 4th or 5th year, then you can use the log rank test. If you are anticipating it in the early part, then you can use the Wilcoxon, and in the middle you can use the Taron-Ware. So it all depends. The graph means your study period, and again there's no cutoff. It's very subjective. And again, all the recommended textbook, they suggest that you should prior think that which test you are going to use. You should not be fishing like what we do. We click all the 3 options, and when we see that which is significant, because there may be a situation where the one test will show a significant level while the other 2 will not be significant, depending on the early, middle, and late period. So they always say that you should avoid fishing for the p-values using all the 3 tests and then select based on the p-value. So ideally, it should be a clinical explanation which you have thought of or which is available regarding the maybe pharmacokinetics and pharmacodynamics of the drug if you are doing a drug study, or if you are using any other study, maybe a risk factor, then also what is the available literature. In what time you are expecting that particular effect to come up. So it is usually decided based on that. So what is this median survival time? So this median survival time is different from the median, which we learn in the descriptive. Like in descriptive, how we learn the median, that you arrange the data in the ascending or the descending form, and then the middle value is the median. That's how we describe. But in this case, this median survival time is different. How it is different? Because we'll see that. But just to explain, in this case, whenever the cumulative survival probability, it reaches to 50%, that means time when the cumulative survival probability is 50%, we call it as a median survival. Now, why do we always use median survival, not mean, in case of a survival analysis? Yes, anyone from the group? Can you answer this? Why do we use this median survival? Why not mean survival? Because in the output, you will see it gives you, okay, so Dhruv is saying skewed data, non-parametric. True, very true. There's one more reason, if you can say, like it is given in the various textbook, that why do we take median survival? This is a correct answer, which all of you have just written in the chat box. But there is one more answer. So one more answer is that for a median survival outlier, that is also true. That is related to that skewed or maybe the... but one more reason is that in case of a median survival, you only need 50% of the outcome to be observed, because you have started with the data, and till the time, if you imagine that graph, we'll see that till the time it has reaches 50%, then you will get this median survival. After that, whatever happens to the survival, this median survival time, it gets unaffected. That's why you only, outcome, you observe only 50% of the outcome need to be observed. That's why you can calculate this and you can give the interim result in between also regarding the median survival time. So now coming to some basic assumptions. So there are few assumptions in case of a Kaplan-Meier survival analysis. So we all know that it is a non-parametric because the length of follow-up, one of the dependent variable is the time to follow up. And this time to follow up, it may range from even 1 day till, in the previous example, 2600 days. So there is a wide range, and that's why it is a non-parametric. And it is also known as the Kaplan-Meier product limit estimator method. And this can accommodate missing data that we all know that because of that only, that's the, there is a difference between the life table and this Kaplan-Meier, because life table, what we do, we take a period. We don't include the exact survival time of the person. So we are not calculating the instantaneous survival, rather we calculate the survival for the whole duration. But in this case, since you have got the time of each and every individual, and you take that as a dependent variable, in that case, you have the instantaneous survival. That means at every time period, you have got a survival, and that's how you calculate the cumulative survival probability. And in this case, you express your result in terms of the median and the standard error of median and confidence interval. So Dhruv, I will explain once again this instantaneous rate. Once I'll show you the difference, because in my slide, I have given the two tables together, like one as a life table and the other as a Kaplan-Meier. Then maybe you can understand in what do we mean by instantaneous. Instantaneous means at that particular point of time. We'll see that. And then median and the standard error of median and confidence interval of the survival time will be calculated. And we compare the survival curve using log rank test or the Breslau or the Wilcoxon or Taron-Ware, depending on the whether we want to see it in the early, middle or late part. So this time to event data, again, we have seen this, that it is unique because independent variable, independent, that means outcome variable. You are taking two variables. One variable is the time of follow-up and the other variable is the outcome. So you don't, like in case of a classical logistic or linear regression, you only take whether the event has happened or not. But in this case, you have seen that you need to enter two variables. First is the follow-up time, and the second is the when that event happened or not. And this logistic and linear regression, they are not suitable for such time to event data, because then you will be losing on many information, and then whatever calculation of the risk which you will calculate, that will be either the underestimation or the overestimation of the actual risk. And then it is important for a type of data which is known as the censored data. When you have got a partial information means you don't know the outcome of the person, what has happened to him, even that, like the duration is for 5 years, and that person, there's a loss to follow up at 4.5 years, 4.5 years. Then if you do a logistic and linear regression, you will simply discard that person. But in this case, because that person is also important, and in that case, you assume that the cause of the censoring, that is not related to the event, and we'll do that. That is known as the non-informative censoring. We'll learn that. And then there are a special technique in that all mathematical formula which is there, like Kaplan-Meier estimation or the calculation of instantaneous or the potential hazard or the survival. All that involves the integration, the concept of calculus and the integration. So that is there in running in the background. So there are some special mathematical technique which makes this data analysis suitable for us. So now there are some methodological issue in these time to event data. First and very important thing, that there should be clear-cut definition of the target event. So in the day one also we were discussing the left censoring. So when you don't have a clear-cut definition of the target event, there may be a case that there may be left censoring. And left censoring is when you have diagnosed that person may have developed the disease long before at the time of diagnosis. So in that case, the actual survival time, it will be less than the actual survival time will be more than the observed survival time. So that we try to avoid, and that's why we were saying that, like in case of a death, or like if you can take any example, recurrence of any disease, and if there is no such because if you just recall the natural history of disease, a natural history of disease has got many phases. Like it has got a latent phase, and then it had got a subclinical and then clinical. So usually you should try to do this survival analysis when those phases are very small, so that that will help you in removing those or minimizing those left censoring. And then the other is the, like in case of a copper T, it is very clear cut. If you say that you want to know what is after copper T insertion and the event to describe that removal of copper T, and if you want to see maybe in the two groups, maybe one person who is obese and the other person who is normal BMI, and if you want to see that removal of copper T, what was the median survival of the women who did not remove the copper T in the obese versus non-obese. So that removal of copper T, it is an event where there is no left censoring, because the moment she removes it, you will come to know that, okay, she has removed, maybe from the data, the record, or from the history also. So that is clear cut. So that we understand by the clear definition of the target event. Then again, you should have a very precise start time and the time of origin and the end or the follow-up time. And we have learned how we can convert, because you enter the date and in Excel, you can convert that in the follow-up time that you have. There are ways in SPSS also to do that, but Excel is the simplest one. And then again, the time scale. This is very important, because the smaller time scale you choose, the smaller will be the hazard and the survival probability. The larger time frame you will choose, larger will be that. But again, it is important to choose appropriate. Like in case of a death, if you want to measure generally, you will see that if you want to be very precise, then instead of years, or you can calculate that in months, or maybe if days are also important, then you can calculate that in days also, days of like even death. So that will be very much precise. So selecting a time scale is very important. And then you have to define that how the participants will exit the study. Means how will you how will you treat the case as a censored case. And there are some competing risks also, which we have discussed on day one. What are the competing risks? That if like you are studying a death event after the episode of MI, and if the person dies because of some other reason, maybe cancer, maybe road traffic accident, so there is a death, but that is not due to the MI. So that is known as the competing risk. That particular reason is a cause of death which is unrelated to the event. So that also poses a problem, because in that case you will have to think that what would happen if that accident would not have happened. So in those contexts, similarly in case of a loss to follow-up also. So you always say that reason of loss to follow-up, that is not because of the cause which is related to the event. Because if the event is like in this case, I was saying that copper T removal, and if you could not have a data of a female, what has happened to her after the copper T insertion, you assume that the reason of the loss to follow-up is not the copper T removal. So do we include the competing event in censoring, or do we count it as a death itself? So we include that as censored event. And there are other ways to do the analysis, but again, right now we are taking those events as a competing risk also as a censored, because the death or the cause of the death, that is unrelated to the event. And then there are, in the JAMOVI also, you will see that there is a multiple. That's why maybe you will see many survival, they include all cause mortality as an outcome. Or there are multiple options also. You can take more than one event also in that case. That is a separate analysis. But again, it is up to you. If you want to do a simple Kaplan, Meier, and Cox regression, you should take that as a censored event. If you want to study multiple outcome, then you can take it as a multiple outcome also. So what are the underlying assumptions for this Cox proportional hazard? So this underlying assumption, the first assumption is that the event status, it should be mutually exclusive. So what do we understand by mutually exclusive? That means either the event should happen or the case should be censored. So that's why we call it as a mutually exclusive and collectively exhaustive. That means you will assign every individual either as a 0 or as a 1. 0, that means censored, that event has not happened, and 1 when the event has happened. Then the second is the time to event, this censorship. This is known as the survival time. So whether the time to happening of that event or the time to happening of that censoring, it should be clearly defined and it should be precisely measured. So that's why the maintenance of data, that is very important. And in the countries where they have a very good database, they usually perform the survival analysis based on the database. They don't conduct a study separately for survival analysis. Like in case there are many programs here where you have good databases, like DOTS program. So you can see, take any outcome, maybe time to default. Person has started the medicine and person of stopping the medicine. If you take that, you can see that you will have a data, and maybe you don't need to go to the individual because you in the NICSHA portal, maybe you have got the data. So that should be clearly defined and precisely measured. So if it is automatically, if it is a web-based or a real-time data, then your survival analysis is very precise. Then the third is your independence of censoring and the event. So this is again important because you assume that the censored data or the censored individual, the cause of the censoring, that is not related to the event. So both the event should be independent of each other. Just to give you an example, like if I'm studying this recurrent attack of MI, second attack of MI in all the individual who had first attack of MI, and if there is a person who is a loss to follow up, so I will assume, exactly I don't know, but I assume that that person, if he would have been in my study, he would have developed that MI maybe at this particular time point, or the reason of his not coming to the study is not the MI. Because that's why you will see many survival analysis, they always, which is based on the data, they say that, we'll share one study with you also, that in that area, there was only single hospital of particular treatment. So if the second attack of MI will happen, that person will go to that hospital only. He cannot go to any other hospital or setup. So that means you know that if there is a loss to follow up, or if the person is withdrawn from your study, if he withdraws from your study, it is not due to the recurrent or the second attack of MI. There can be a case like if in my hospital, if in AIIMS, if I am trying to do something, maybe I want to see the knee replacement, at what time after knee replacement the person has started ambulatory, become ambulation. So maybe if after 6 months, if the person has stopped coming to me, and if he goes to some other hospital, maybe there are many hospital or many private practitioners. So if he goes to any other private practitioners, and maybe that early ambulation, or maybe he become not non-ambulatory because of any other reason. Maybe he has got some fracture again after there was a fall and there was a fracture. So he again had some other event. So that's why we assume that the censoring and the happening of the event, that should be unrelated. That should not be related. And we assume that that person has, if he would have been there in our study, he would have experienced the same event at the same instantaneous rate. So this underlying assumption, we always say that the left censoring should be avoidable. So Dhruv is asking, do we include the competing event? Yes. Oh, I have answered, sorry. So underlying assumption is that the left censoring should be avoided. And that we have discussed that if you have clear-cut definition of the event, then usually the left censoring is not there. Then the next concept is the secular trends, which is also known as the secular changes. Now, what is this secular changes? So these secular changes, they affect the right censoring as well as left censoring also. Now to understand this, let's understand with the one example. It is given in many. Okay, I'm sorry. So this secular trends, now what is this secular trends? Like if your study is a very long study, maybe for 10 years, so there may be a situation where there over a period of time, the treatment method or the diagnosis method, both has changed. So if you are like the same research question, if you are like after the first MI, what is the time or the event of the second MI or the recurrent event? Excuse me. In that case, like if a new treatment, like there are many treatments which usually come up after the first MI. So during the course of time, you have started recruiting all the individual, but you don't recruit all the individual at single point of time. Like in a period of maybe if your study period is 5 years, you decide that up till 1 year I'll recruit and then I will not recruit. So maybe you have started recruiting and after 6 months you have seen that there is some new treatment which has come up for the treatment of this MI, post MI. Maybe that ACE inhibitor which reduces the incidence of the second MI. So if there is some treatment modality changes over the period of time, then definitely your censoring, especially the censoring that the happening on the event, because one of the censoring is right censoring is also that till your period of study, that outcome hasn't happened to that person. So if the treatment has changed and if the person has started, those of people who have started taking treatment after you have recruited after 6 months, then maybe in one group you will have early onset of MI, in the later group you will have late onset of MI. So that will affect your right censoring. So in that case, if that is the case, then you should perform two separate analyses, one before introduction of that particular treatment and one after introduction of particular treatment. Because if you do it collectively, you may have a overestimation or the underestimation of the survival time. So that we mean by the secular changes. So there should not be any secular trends in the diagnostic criteria or in the screening procedure or in the treatment. And all these assumptions which we have discussed up till now, they are a study design issue. So you cannot calculate that in the SPSS. And again, there's one more assumption, that is there should be similar amount and pattern of censorship per group. That means we'll see what is that. That is the SPSS statistics. We check it by the SPSS statistics. So if there is a secular change, there should be analysis of two different time points. We have discussed that. So coming to this Kaplan-Meier method. So like in this case, you can see there is a one individual who died at 4 months. So you will calculate the survival at 4 months. This we mean by the instantaneous calculation. You don't calculate it for the period. Like in life table, you calculate it for depending on the period. Like if it is a 1, 3, 5 year, then you calculate 0 to 1 year, 3 to 5, and then 5 to 6. But in this case, you are calculating this survival at time t. So you started with 6% and 1 person died. So what will be the survival? So 5 people survived. So survival will be the 5 by 6 and cumulative survival that is applicable for the next case. So in the next case, 1 person died at 10 months. And there is another person who is a dropout. So the number of cases, you have to remove 2 cases. So 3 cases left. In the left means survived, because 1 died and 1 there is a left out. So 3 cases left. So what will be the cumulative probability at 3 months, that is survival at 3 months? So it will be the 3 cases, and you reduce this 1 from the denominator because 1 person is a loss to follow up. So you do 3 by 4. So there is a 0.754. So remember, this is different from the life table, because in life table, you try to reduce half from the denominator. But here we are reducing, like deducting the complete one, because we exactly know the time when that person has lost to follow-up. And then you can see that one died at 14 months. In that case, what will happen? 2 will left. There's no loss to follow-up. So 2 by, then again, there are 3 cases which survive. So 2 by 3, it will be 0.667. Now, if you see, this is the instantaneous survival group, which we were talking, that you are calculating the survival at time t. And then when that event has happened, and you assume that the person has survived up to that event, and then you calculate the cumulative survival. So the cumulative survival is always multiplicative. So this second survival will be the second cumulative survival. If you focus on this, then you can see that this it will be 0.833 into 0.750. And then similarly, if you see this one, this will be 0.625 into 0.667. So what you do, you multiply these two. If you see this, you multiply this 0.67 and 0.625. Because from previously, this is the probability at 3 months, maybe, yes. And this is probability at 14 months. So this first one is the probability at 4 months. This second probability is at 10 months. So if you have to calculate cumulative probability, what will you do? You will multiply this probability 0.833 with the 0.750. Similarly, if you have to calculate the probability at 14 months, then you will multiply this 0.625 to 0.667. And if this person died at 24 months, so, and there's a one loss to follow up. So there will be 0 in the numerator. So the survival is 0. So the cumulative survival will also be 0. So this is how we calculate the graph. So in this case, I will explain you this once we'll see the this Kaplan-Meier, this survival in the SPSS. So maybe I'll come to this slide later on, because then you will be, or else I can explain it here also. So remember, this is the life table. So life table, this is the same life table which you people, which I have shown in the demonstration. And there you have seen that this was the 11 number. So this 11 was the withdrawal. And that's why I have deducted 5.5 from the denominator. And that's how I have calculated the survival. So if you see, in case of a life table, how do we do? Basically, we first that 50%, because we take it as for a period. So for this, you can see that this we took from the this 2 by 65.5. So this will be the event, but proportion surviving, this will be the 63 point, because you will remove this 2 from the numerator. So the proportion surviving will be the 63.5 by 65.5. Similarly, if you have to calculate, so this is for a period. So the first one you are calculating for the 0 to 365. The second is you are calculating for 365 to 730, means for 1 to 2 year period. Then again, this number withdraw during the interval, that was 13. So I'll deduct again 6.5. So 6.5 and then 2 event has occurred here. So 8.5. So I have deducted 8.5 from 65 and this comes as 51.5. Number of events were 5. So if you do 5 by 51.5, so how much left? So this also 5 you will deduct it. So it will be 46.5 by 51.5. But this cumulative probability, this is the multiplication of the first probability multiplied by the second probability. This is there, in the background, this calculation is running in case of a life table. But in case of a Kaplan-Meier or the survival table, you will see that you have exact time. In this case, you don't have time interval. You have 19 maybe 1900, what this maybe time 19 days or maybe 61 days, 100 days, 101 days, 116 days. So you can see that at 90 days, we have started, maybe this is for the male. So there were 70 males. We have started with the male, 71. And then we see that one, there's a one which is a censored. So this doesn't give you, in case of a survival, this life table, this column gives you the number withdrawing during the interval. That means censored. But for this survival table in the Kaplan-Meier, you will not find a column of censored individual. So here it is, there are 71, but if it is 70 here, you will assume that one person has this you can see censored. Then again, there is a second attack of MI. So how it will be done? So there are now 69 individuals left because one person had an attack of MI. So how you do? You do the 69 divided by 70. And that comes as a 0.986. Similarly, if you come to this third one, so this is a censored. So whenever there is a censoring, it doesn't calculate the probability. It calculates the probability of the event only when that event has happened. And the one minus that event is the survival. That's how we have learned. So what it does, this, it will not calculate anything, any probability here. This will be the same. This you can, that's why you can say that this 0.986, the cumulative, it is same for this also, for this also. Now it is 0.971. So how this 971 has come up? Because at 116 days, there was an attack of MI. And at this time point, you can see the remaining cases are 66. That means again, you can see that 2 events have happened. So 66 event was there. And this 2 is the cumulative. Actually, 1 event has happened. That's why the total remaining case is 66. And there is no censoring. So this 2 is the cumulative. That means 1 event at 61 days and the second event as 116 days. So there are 2 events. So how you calculate the probability here at this time point, 116. So this will be the 66 divided by 67. And when you multiply these two, that means you multiply this 0.986. That means this was the 69 by 70. With this 66 by 67, you get this 0.971. You can all do in your phone calculator. You will find the same number. So that's how you get a cumulative survival probability in case of a Kaplan-Meier. Have you understood this? Okay, Dhruv, Saurabh, Radhika. Okay, thank you. So remember this, this remaining. So always the cases which remained at the time of event, you will take that as a numerator. And just before that, whatever was the surviving, you will take it as a denominator. So this was again, this was a survival curve for this one case, which we have done here. Before this, this example, which we are saying at the 4 month and then 10 month, 14 month, and then 24 month. So this is the survival table of that there is at 4 month, there is a death. At 6 month, there is a censored. At 10 month, there is a death. At 14 death, and there is a 24 month at death. So this survival function, this comes as a stepwise function. So in this case, whenever there is a drop, you will think that there is a event. And when you see this dash, then there is a, you can say that there is a censoring. And that's how it has written here. This is like a censored in any survival. This is a censored one. This you can see. So this is a censored. At 6 months, you remember there was a censoring. And at 18 months also there was a censoring. And this drop, this whenever there is a drop, that means there is a drop in the cumulative probability. And that is because of the event. Because whenever there is an event, then only the cumulative probability will be dropping. So this drop line is the survival function. So now in SPSS also, to detect the amount and pattern of censorship, you determine the scatter plot. You do the scatter plot between the censored data and the non-censored data. So SPSS command, if you've got a statistically significant difference between the survival function, then you can carry the pair-out comparison, pairwise comparison if you have got more than 2 groups, 3 or more than 3 groups. That we'll see maybe today. We can show it on the BMI and then you will see how to do that. So I'll just show first in the SPSS how to perform that. So this is my question. So in a study, the researcher followed 192 cases of the first attack of MI for 7 years. The second attack of MI was taken as an outcome. It was observed during this period where 0 was censored and 1 was second attack. 70 patients had second attack of MI all over the period. So the question is, we have to calculate the median survival time for second MI across gender and determine that there were significant differences between the survival distribution of second MI across gender. Again, I have to see what is the median survival time in race, and race because race has got 3 categories, and across BMI because BMI also has got the 3 category. So we'll just demonstrate comparison of 2 by log rank or this Wilcoxon, or comparison of 3 or more than 3, then because you can see the pairwise comparison. So this is my SPSS sheet. So I'll have to see the assumptions also because we have seen that there are assumptions. So we have seen that the 5 assumptions are the study design issue. That the first one, that either it should be mutually exclusively or collectively exhaustive. So if I see the follow-up status, this is the follow-up status. And if you change this, you will see either everyone is a second attack of MI or censored data. So either it is 1 or 0. Then you can see this is the smoking, yes and no. This is the follow-up duration in days. This is the BMI category, which has been categorized as the underweight, normal, and obese. This is the MI type, Q wave and non-Q wave. This is the order, like recurrent order or first. You assume it to be first order. And then CVD, race, gender, and age. So this is the data set. So now you can see some filter. So I will just be using first assumption. The first assumption was that then other like secular changes, and there should be independence of censoring and event. That is also a study design issue. So on SPSS, we check that for the amount and pattern of censorship. So how to do that? First, you have to select the censored data. So you all know how we select the cases in SPSS. So go to this file. In file, you can see. So sorry, in data. In data, go and click on the select cases. So select cases, you have to click that if condition is satisfied. And if you can say if the follow-up status is 0. 0 means that they are censored. So I'm selecting all the cases which are censored. Press continue and then press OK. So if you have pressed OK and if you see the data set, you can see something of this. So this has cut these slash lines. This shows that this will not take these 1 cases. So now only analysis which we can perform is on the censored data. So now you have to plot a scatter plot. Like in the first case, it was gender, and we have to see that the censoring, it was same in both the gender, male and female. Because if the amount of censorship and the pattern of censorship is different in these 2 categories, that will affect your survival. And if you compare these 2, then it will not give you the true picture. Because ideally what we think that if the pattern means like if you can divide that 5-year period, if my study duration is of 5 years, if you can divide that hypothetically in maybe 3 duration, then in each and duration, the pattern of censoring means that if you see the graph, the scatter plot should be in the 1 line. We'll see that. And amount is that is yield in the SPSS output that we'll see. So I'll go to the chart builder. Then I'll select a scatter plot. So I've selected the scatter plot. Oh, sorry. Actually, I have to reset this. I have selected this scatter plot. And I have pressed OK. So now this X and Y axis you can see. So on X axis, it will be the follow-up duration. And on Y axis, you have to take the categorical variable across which you have to plot the KM curve. So KM curve, right, my first question was, I have to compare it between the gender. So this gender will come on the Y axis. And until this outer border gets red, that means it has come up to this. So now if you press OK, and if you see the result, you can see the result of the scatter plot. So it shows you the scatter plot in first 500, 1000, 1500, 2000, and 2500 days. And you can see that almost pattern of censoring. This graph, it shows that this picture, there is no like any sense, no point which is going up or down, and it is usually in the same line, both. That says that the pattern of censoring was same in both male and female. Now, once you have seen this amount, we'll see in the output. So now go to analyze. Now, before you go to analyze, you need to deselect all these cases, because right now you have applied a filter. So again, go to the data and go to the select cases. And in select cases, you, instead of this condition, you click on all cases, press OK, and then you will see that all cases are selected now. This has removed, this got removed. So now go to the analyze and go to this survival, this Cox regression. Sorry, I don't have to tell you the Cox today. We are discussing the Kaplan-Meier. So we'll go to this Kaplan-Meier. I have reset this. So like we have seen this in the last class also. This follow-up duration, you will move to the time. This final status, you will move to the status. That shows whether it is a event is censored or it is a event or a failure. Then you have to press continue. In the factor, you have to press this gender. And then you can see the compare factor. In compare factor, if you are assuming that which early, middle, or late part you will see, but if you're not sure, you can click all three and then press continue. Coming to the options, you can see this survival table and median survival time. You can click on this survival table, press continue, and press OK. Then you can see the survival table. So the first is, it gives you the case processing summary. So if I come here, if you see this, this is the case processing summary. It tells you that there are 71 males and 122 females. And the number of events were 19 in females and 51 in males. And in censored also, you can see the amount of censorship. So in female, there were 73% censored data were there. That means more censoring was there in the male, and less censoring was there in the female. So amount is not same, but still you can say. And again, you can go to this thing, descriptive, and you can check for the significant chi-square also. But right now, don't need to do that. If you see that this is like 73 and 58%, you can report it and you can take a decision to go with this Kaplan-Meier. And this, if you come down, so one thing is that you have to report it. So you have to write that there was 73% of 73.2% censoring was there in the male, and 58.2% of censoring was there in the female. And then if you come down, you can see here that this is the same table which we have discussed. So in the first one, if there was one censored data, that's why number of remaining cases is 70, because you can see there is a one censored. So this there is cutoff. No, there's no such cutoff how much censoring it is good or bad. You can check, like what we have seen, that you can go and check. Like what we can go see. I can go again here, and You can again select cases. So go to data, select cases, select this follow-up status, press OK. Now I'll have to see whether the filter has been applied or not. So yes, filter is there. Now go to analyze. You can check with the descriptive also.
Ma'am, actually the entire screen has not been shared, I think. The output window is visible, not the comments.
Okay, right now I'm showing the output only.
Okay, ma'am. Okay.
Okay, so that like you can see in the column. So which is the dependent? Independent is the gender. So I can move gender here, and in column you can do that final status. And then you can go to the statistics. You can put chi-square, continue. You can see here, this value, no statistics are computed because final status is a constant. This 123. It is not giving, but I have seen that you can calculate.
Filter is already applied. That's why the answer is not coming.
Filter applied.
Okay. Let me go. But I only want that censoring. Now that's why I applied filter. So okay, yes. Let me check. You are right. You are right. I'm again going and I'll go to the data. And I'll go to this select cases. Yes, you are right. All. Okay. And then if you go analyze, if you go to the descriptive, cross tab, statistics. Okay, so you can see this maybe that it will give you that it is significant. So that maybe amount of censoring showing that it is significant. But still, at this juncture, what you can do, similar amount is no. 1755% is not same. It is like we can say that there should be plus minus 2 to 5% difference, although it has not been mentioned anywhere. But I've seen classically that people, they do mention in many literature or many publication, you will see that they have not mentioned exactly regarding that amount of censorship. So pattern, that is important. Amount, if it is there, if you are finding it significant, like in this case, there is a significant difference. So in that case, you can take a call and you can report it, but still you can apply that Kaplan-Meier because that reader will understand from that perspective. So that's why we have told you regarding the amount also. And but again, that is we can say that this is significant. So go to then again analyze, and then so Kaplan-Meier, we have the output, I guess. So we can again see that only. So let me go to the output. I'll go up. And then I can see. So this table we were discussing. So this was we have discussed that in that PowerPoint, which I have shown you. That it gives you a huge table, this SPSS, of all those individuals which are there in your case, like male and female, because you have applied it across a category, and it will give you the probability at each and every time point when it is censored. So you can see when the person is censored, that there is the same this thing probability, and when the person is not censored, then you can see there is a, like in this case, you can see this is 444. So the this thing. So these ideally this table, it is not needed in the manuscript. So this is just for understanding. So you can again take a call in the analyze option. You can uncheck this also, because this comes as an option. So you can uncheck this survival table. Excuse me. And you can take a decision not to have, because that table is very huge. So now you can see the mean and median survival. So now, can anyone explain this median survival time? how to interpret this. Yes. So which one is more? The median survival time, it is more in female, or like 50% of the female, they survived up till 1914 days. Whereas the male, they survived longer. It is 1926 with this 95% confidence interval. Yes, so it is more in male. And this chi-square, this log rank value, it is again expected, calculated basis on the expected, this chi-square, because it calculates the observed survival and the expected survival. And how we used to have calculate, that is the observed summation of all observed minus expected square divided by the expected. So that's how you calculate the chi-square. And this, all the values of the log rank or Breslau, that is actually a chi-square statistics with 1 degree of freedom, because there are 2 categories here. You can see here significant level, all the 3 are significant. That means if you see the graph, you can see that they are like in the initially also. In the initially also, so median survival time is more in male. Yes, Raghavendra, you are right. So this is in the early part, it is also like you can see it is not never crossing. In this part also, here you can see that there is a crossing, but still that you can comment that that's right, maybe it is, but again, you can see that all the tests are significant here, all the 3. So this is, you can paste this graph in the result, and JAMOVI also you will see that in this case you can plot n time, it is 2500, because that much I have maximum time was 2500 days. So that's why it is like that. You can change this graph also. We are not going into the detail of that changing. That's why the log rank is least significant. Yes, because they overlap. Because log rank is for the last part. And if you see the values, this is the least, this 0.02 is the least, the highest value of significance. 0.009 is the Breslau-Wilcoxon. So this is in the initial, and this 0.01 is also in the middle. So this is again a chi-square statistics. We know that. So I have to explain this point once again. So which point, Dhruv? Like explaining this graph or median survival? Can you please again type? Okay, interpretation of graph. So interpretation of graph, if you see this, see there are 2 colors. So there is a green one, which is for the female, and there's a male, which is, there's a blue, which is for the male. So higher the curve, more the survival. So like, how will you calculate the median survival? If you draw a line here, maybe I would have, let me try to draw it. So this is somehow 50%. So I am drawing a line here from 50%, and I will see where it will cut. So it will cut something. This is very thick line. This is not as thick. And similarly, if you come to this male, it will cut something around here. So you can see that these are the difference between the median survival time, because this is 50%. So you draw a line, and wherever it touches the graph, you draw a perpendicular line. And in that case, this time which you are seeing here, that is the median survival time for female, and for blue one, it is the median survival time for male. Now coming to the other interpretation, this you can see here, this early part is separated, this is also separated. Later part, it is separated, but again, like Pragya is asking, if the log rank is significant, how can be the true curve overlap each other? There might be some difference between the small, but not overlap. Actually, this depends on the axis also. Like if you increase this axis, maybe this will be wide apart. Because if we expand the graph, that we have not done here, maybe if you increase it, this will be separated. So then we can see that this is the, no, not the curve which you are seeing here. So this is more objective way. If the log rank is saying that it is significant, that means it is significant. You only need to change the pattern or the axis of the graph. And then probably if you can expand this, you can see the graph. So this was the interpretation. Now, if you come and see here the mean survival time. So you can see the mean survival is 1772 and 144. And there is a difference between the mean and median. But we have discussed that although SPSS gives mean as an output also, but we always write the median survival time. So how do we write this? If you come and see the write-up. So we paste the table like this. You can have more than one outcome. So this is the graph, the same graph. Change of axis, yes, I will explain. I'll explain later. And then you can see this mean and median and 95% confidence interval. So this is the median for female and this is median for male. And then this log rank value is significant. You can see that for gender, how this JAMOVI is giving. So we'll see the JAMOVI also. So for JAMOVI, you have to go here. And this was the interface of JAMOVI. You have seen this. So again, I'll move this back. This follow-up status. So this JAMOVI interface, you can see, go to this survival. This survival, you have to choose this univariate survival analysis. And then this is the time elapsed. So move this follow-up duration because it's a scale variable here. And then follow-up status here. And this follow-up status is the second attack of MI. And then you move this gender to this. And now coming to this thing, you can do the pairwise. Obviously, pairwise, we do it for more than 2. That we'll see with the BMI. You want a survival plot. And for that plot, you want this 95% confidence interval, censoring and risk table also. If you don't want life table, I think you can remove this. And then it will give you so this is the median survival time 1926 and 1426 with its standard with 95% of confidence interval. I said that it gives all three together. So we are not discussing Cox regression now. We'll discuss it day after tomorrow. And this 135-year survival also it gives you. Although I have cut it, but it will take it as such.
We don't.
Okay, sorry.
Any issue? Any questions, Marnika? Okay. So if you can see the graph, this graph is like this with 95% confidence interval and log rank is significant. It is 0.02. And this is the number at risk, which it gives in the base that 71, 70, 70. And then this is for the gender. And then how it calculates the cumulative survival. So now coming to the second question. The second question was across the race and BMI. So if you have to do the write-up, how will you do? Like I have written that 192 patients were followed up for 6.5 years, 71 male and 120 female. And so Shivaji is asking, is survival analysis possible because adding the factor to see cumulative? In JAMOVI, it is not. In JAMOVI, if you don't put a factor, it will not give you. You are right. But in SPSS, you can do. That's why, you need to know more than one type of software. Because I said that there are few things which is good in one software. There are few things which is good in the other software. So if you know both, then you can complement like one part which is missing in one with the other part. So you are right, Dr. Shivaji. If in JAMOVI, if you don't give the factor, it will not give you the overall survival. Yeah, that's true. So then you can see that I have written that Kaplan-Meier survival analysis, it was conducted to compare the median survival time across gender. The pattern of censoring was same, but amount of censoring was different. And the female, they have 12 days less median survival time than male. A log rank test was performed and it was significant. That's how you will write. And then coming to the second part, that was across the BMI and across the race. So if you go to the analyze again, go to this survival, then Kaplan Meier, instead of gender. But there is a problem here. In factor, you cannot have more than one factor. And that is the advantage with Cox regression. Because in Cox regression, you can put multiple factor here. So it will be an adjusted one. Here, it is only give you the against to this thing. It will not be adjusted one. That's why you need to know the Cox regression also. So instead of gender, now I'll put the BMI category. So for BMI, now you should be using this pairwise comparison because there are more than 2 categories of BMI. And then you can continue the save, come to the option. I am not clicking this survival table because it will give you the very huge table, which we don't put in the as an output in our research. Then press continue and then press OK. So once you have pressed OK, you can see the median survival time. So if you focus here, you can see that the median survival time, it is more in. This is the median survival time. So it was 1979, 1914, and 1325. So median survival time, it was more in the obese, and it was least in the underweight with its 95% of confidence interval. And if you come down and see the pairwise comparison, so you can see that between which pair it is significant. So you can see that this is comparison between normal and underweight and obese. So this is significant, this value, 0.007. So you can see that this 0.007 is significant. So this you can see that obese versus normal is significant. Similarly, the other significant is this. This is also obese versus normal. And this is the underweight versus obese. So obese is significant with both underweight and obese. This is the pairwise comparison using log rank. And similar thing you will find in the Breslau and Taron-Ware also. And this is the survival function. So you can see this was for the obese and these two for the underweight and normal. That's why you will see these are more often are crossing each other. So that's why these two are not significant. But yes, underweight with obese and this normal with obese. So you can see that they have got the this one, but you can see that the median survival time, that is more for this obese. And there was a question that we have to report all three or only log rank. Generally, you will see that what usually we do, we report the significant one that we have seen in most of the article. But you can report all three also. That will say that will be good for the reader to guess that it was significant in which part. That you can do that. Either report all three or report which is important for you as a clinician or as a researcher. But just don't mention one which is significant and leave the other two. If it is not your intent. That's what the classical textbook like Lindbaum and they say, that you should not be fishing for the p-value, significant p-value. So what I would recommend, you can give all three so that the reader will understand like early, middle or late part or whatever is a significant. So this is more than 2. But if the data is ordinal, then you can use one more option which is here. That is for the trend. So in our case, we don't have an ordinal data, but if you want to show something like a trend, then again you can go to this Kaplan-Meier, and instead of this, in comparing factor, you can see here, there is a linear trend for factor level. You can click that and you can see that also. So for ordinal data, it will show you that there is a linear trend like increasing or decreasing, whatever. That option you can use. But again, we are not using this for today's session, and we are only comparing the 3 groups, more than 2. So coming to the same exercise in the JAMOVI. So go to JAMOVI if I have to perform the same. So what I'll be do? You put that in gender and then come to this BMI cat. And there you will see and in the pairwise comparison here, you have to. So, okay, here why this graph was coming like that, because if you do this 2500 and write this 365, maybe like I'm dividing it in years. And if I remove this 95% CI, then maybe appearance of the graph. Yes, so now we can see it's a little better than the previous one. This graph, the previously it was not appearing. So yes, we can see that with male also. So instead of this, if I put the gender, then also the so this is important, this function. If you want to improve the appearance of graph, then this graph, this option, this plot argument, plot end time and interval time. So we have kept like interval time as 365 days till 2500 days. So that's how, and if you have to write the interpretation, so what I need to do, I need to open an updated table. So I'll just close this. So this was against, like you can see here, median survival time. Excuse me. It was less for obese, followed by underweight, and then, excuse me, normal. I'm sorry. And then this is a pairwise comparison. So you can have a like levels normal and underweight, obese and normal, and you can see the p-value. So this is the only significant, the obese versus normal. The rest of the two, they are not significant. And this is the graph. Similarly with the race, you can see. And this is the write-up that in 192 patients, we have followed them up for 6.5 years. There were 25 obese, 40 underweight, and 92 normal BMI person. Kaplan Meier survival analysis was conducted to compare the median survival time across the BMI categories. The median survival time was the lowest in obese group, normal in an underweight group, although there were no trend in the median survival time across BMI, but pairwise comparison clearly depicted that median survival time for the second MI of person with normal BMI was significantly different from obese, and Kaplan-Meier showed curve the same log rank value. So this is how you write the interpretation. Now let me try with that SPSS. You want to see how to increase that, maybe.
Madam, what is meant by NAN in confidence
So
interval?
that NAN, that is, yes, in JAMOVI, that is coming. We tried to, maybe that upper range, it is not showing. We have seen this, we tried to see this, but I don't know why it is not coming. Exact reason we are still exploring why it is coming like that. But you can take the value of SPSS. JAMOVI, there are few problems because still it is evolving. That's why we are saying that value, upper value is not coming. We could not crack it. Why it is coming like that? Maybe give us some more time and we may tell you the reason. But right now, I don't have an answer. We were looking up for this since morning, but we could not do it. Maybe people can also try, and we'll also try, and maybe by day after tomorrow, we should be able to tell you something.
Okay.
And in the meantime, you can use the value of SPSS because that gives you the upper one also.
Right.
Ma'am,
Yes.
Ma'am, in case of ordinal data, we have to put the linear trend.
No, it's up to you. You can put, or you can go with because ordinal, you can treat it like if you want to see the pairwise, you can have that pairwise comparison also. But trend, if you want to show a trend, Like if there is ordinal, you can go for that option. In
Then
our
ma'am,
case,
how
yes.
to interpret that case?
See, now I'll apply once. It will only give the one value of log rank. I'll show you. So you have to go like in this case, analyze survival. So like in my case, if I treat that underweight BMI category, maybe that underweight, normal and overweight as a ordinal data, obese. So I can go with this compare factor. And instead of this pairwise comparison, I may click this linear trend, one factor, continue, and then press OK. So now if you see this, it will give only a one value of chi-square. And this median value will be for a trend. Like this will be same exactly the median value. This trend is only for comparison that if you see, this all three are significant. That means that there is a less in the obese followed by the, but in this case, you will find that there is no trend. Ideally, what should have been there? Like this obese followed by normal and then underweight. Because this ordinality should have been maintained here also. Just a sec. If you see this, so trend we apply when you see that there is a trend exists here also. But here you will find that there is no trend. 1325, then in underweight it is 1914 and normal it is 1979. So had it been like 1325 followed by this normal and then underweight, because then it will preserve the ordinal nature, right? The underweight is the least, normal is in between. And then, but this median survival time, this is in the middle, it is showing the large value. So this is not a trend. So if you see that in descriptive, something of this sort is existing, then you should do the pairwise comparison rather than trend. If you see that something is increasing or decreasing across the category in an ordinal category, then you can choose to apply this trend. But in that case, trend, it will give you only one chi-square value. I mean, that only one value of Breslau, it will not do the pairwise comparison. Is it okay?
Okay, ma'am.
So in this case, when log rank test is being applied, then which cases are being compared? In which case through, like this, in the case of this trend, this trend gives you the increasing or decreasing, the way I have said. Like if this obese was the least and then followed by the normal and then underweight, it shows you that the median survival time trend. But since that is not observed, this is giving the value, but it is taking maybe that overall significant, not as a, I don't think it is giving you the, because trend is not existing here. So in this case, when the log rank test is applied, yes, the table that does not compare categories pairwise. Here it is not comparing, it is giving you just the trend. It is significant, but it is giving you the overall this thing, because there is no trend as such, if you can observe the median survival time. So ideally, trend should be applied when you can see something in the descriptive, like median survival time. If some trend you can see, then you can go for this, or you can do both pairwise as well as this. You can take a call. So this was the thing. And then maybe increasing the axis. That's what you said in SPSS. So in SPSS, you can explore. Actually, I have also not, but here you can increase the x-axis. Let me do that. So maybe x-axis, if you do the increment, like if it is 500, or maybe if the chart size less, let me know. So let me do it, maybe if I do it to 800, and let me do it, apply. And if I close this, there is a little still increasing, that there's a little, you can see little overlap at two places. Because of that, maybe that is 0.02, but still it is significant, because many people, they say that log rank is overall. See, in literature, you will find that there is a varying degree of ambiguity. I have seen few books where they are saying that you can say that log rank is overall, although we know that log rank is for the later part. So later part, if you think, so for the most of the later part, it is separated only. At few points, since it is like touching, maybe that's why it is significant. Otherwise, log rank, here it is significant. So in spite of increasing this axis, where is that? You can see that there is this one. So if you see the time, it is 2000 days, 2000 to 2500 days. So it is in the later part, maybe. You cannot say, because obviously, but this is again subjective. I'm not saying that this is a very objective, because there was one question. So if you can divide it like 800, maybe you can see that 1/3, maybe from 1600 if I take. So from 1600, you can say that this is quite apart here in this area. If you focus on this area, this is quite apart. So because of this wide apart, this overall value of this log rank, this has pulled up till 0.02. Otherwise, if it would have been very near, then the p-value would have been more than 0.05. Are you getting it? So this near, this proximity, see, there are, I mean, I'm not saying that it takes an average, but there is a proximity in this area. Again, it has got separated in this area. You can see in this area. So there is a proximity for some point, but in the later part and in the beginning, it is quite apart. That's why maybe the p-value that is pulled up to, it has taken the overall p-value as 0.02. Did you get it, Pragya?
Yes, ma'am.
Okay, so you can change the size, chart size, and then you can have this. So that's how this p-value, it is, although it is coming 0.02, in the smaller version, you can see that they were quite together. So we can take, and then, no, there was one more question of that JAMOVI of assignment. So that was, Venkatesh, that was one question from your side, right?
Yes, ma'am.
So if we go to the, on day 1. Okay, so there is a, so in JAMOVI, if you have to apply this, so I'll go to this survival, univariate, then go to this follow-up duration here, follow-up status, event level, explanatory variable, and in the time period, started from 0. So if I do the survival table, so it is 0, 7, 14, 21, 28. And this was the case. So if you see here the number of events, so your question was why the number of events are more than the number of people at risk. So actually this number of event, this 35 here, for this at risk, sorry, this is at risk, 85. So it goes like that it started with 82 people because it is in a period, right? So it is 0 between 7 to 14 and between 14 to 21. So between 14 to 21, it started with the like 82 and then 35 individual, they remained because 12, there was an event in 35 and rest, it was censored. So ultimately after these two, only 12 remained. So it is not like, you can't compare it like in a single line. Is it okay, Venkatesh?
Okay, ma'am. Okay. Thank you.
So, after the 5-minute break, we can go to the breakout room screen. And we can see, sorry, I have to see in the JAMOVI, right? So if this is the graph, and if I have clicked on the 95% confidence interval, here you can see that it shows you like what is the survival. So this again, here, if you come up in the survival, this table doesn't give you that individual survival and the confidence interval, but that probability which you have seen in the SPSS. So for each time point, it gives the 95%. And that's how it plots it. So that's the, probability, and it's 95% confidence interval.
Oh,
So any other what interpretation, like you want to interpretation of that mean survival time or what? Because this is ultimately the cumulative, this is the cumulative probability. And this is the confidence interval of the cumulative probability. Here that 95% confidence interval, that doesn't come.
Madam, another query is there. What is the, how will you calculate whether it is applicable for non-parametric test, that standard error of median?
Standard error of median. Let me come up.
what I
Just a sec. In the JAMOVI?
You have explained in your PPT one term, standard error of median. So I want to, because usually when we are expressing in literature, it is median plus IQR or range is given. Standard error is acceptable or not? I want to ask.
Just a sec. Let me see that graph. Yes, it is there. In the median survival time. I'll perform the analysis once again. Wait. So maybe if you go to analyze survival, Kaplan, Meier. Okay, this you are asking. Standard error. And the lowest and highest. This one. Standard error, right? Are you asking this standard error? I think is.
Yes, ma'am. Yes,
Okay.
ma'am. Okay.
Yeah, so this standard error actually, this is applicable in this case because this median is not that median which we learn in the descriptive. This is the median that at this 0.5 probability, the cumulative probability. So that's why I made an opening statement that don't confuse this median with the median which we read in the descriptive. There
Okay.
Did you get it now?
Yes, ma'am. Yes, ma'am. I get it.
Madam, I have a query. If you plot the survival plot with 95% confidence interval, there are plenty of overlap. So,
Please repeat your question.
Am I audible?
Yeah, you are audible. Sorry.
Oh, okay. So, if we plot the survival plot using 95% CI, there is plenty of overlapping that is seen.
That is there.
But is it very trustworthy? Because the graph is saying that it's not really very significant, but we have a p-value that is saying that it's largely significant. So
we have to go by the p-value. We have to go by the p-value. And again, that graph, whichever you are seeing, that maybe again we have discussed that it's due to the axis and the other problem also. Like if you separate it or maybe enlarge it, it will not be there because it's very narrow, this thing. That's why it is appearing that, there is a quite overlap between the two. But ultimately, you have to go by the value because that is more objective way.
So is it recommended that we do not show the 95% confidence interval in the plot?
Yes, you can remove that. It's up to you. So then it will be visible. And in most of the article, we will share. I have shared the article with them yesterday.
Yes.
Live table. You will see that generally they don't plot this 95% CI. It's usually the line and this step ladder pattern of graph. Because of the problem of access, because it may give some wrong idea. The like we are thinking now that it is not significant because the CI is overlapping.
Yes, ma'am. Okay.
Another question is, what if the pattern of censoring is not equal? We need to report. So right now, yes, you need to report it that it was pattern was same in both or pattern was different. And I did not check for the 3 group. I did not check for the 3 groups. So for if you have to do across BMI, then again you will do it for 3 groups. And then you can write in the discussion. This will be a matter of discussion. When we write our result, you can say that whatever finding you have got, that may be due because the estimate which you have gotten, your pattern of censoring might have had an impact on this outcome. There are ways to tackle that also, but we are not going to that discussion now because that's a little high, this thing. So for all of us, like we consider ourselves as a beginner in survival. So for us, I think we should write, and maybe as a limitation or in discussion, we can mention. That means we know that this problem exists in our data or in our analysis. That's the most important thing.
Madam, is it also an option that if the censoring pattern is not same across the groups, we can restrict ourselves to the live table only because it does not have such assumptions while performing?
No, but again, you need to, because ultimately these days live table has got a very less credibility and the options too. It's better to perform KM and the Cox proportional hazard also. In Cox proportional, you can control for it because that's not the assumption for Cox proportional. Okay. So because in Cox proportional, there is this censoring is not an so if you are performing only KM, then this is assumption. If you are performing Cox proportional, then it adjusts for these outliers and this pattern. So ultimately, we don't stop at KM. We are going stepwise, but ultimately we come up till hazard ratio and in its interpretation. Because that's the only, that's the thing which will help in the policy making. Like whatever drug you have to tell the strength and the effect size also. So ultimately.
So we do all the 3 analyses together and report
Usually live table we have seen very limited. Because we used to do live table before this KM. But if you have got exact time, why will you go for live table? You have got exact time of follow-up. There's no point going for live table. So it's better that you should apply this KM and Cox.
Okay.
And report it. That's better because KM ultimately it will also give you the instantaneous this thing and you have got the exact time of follow-up. So you are not mentioning it as a range. So, and then again, Cox proportional. So most of the articles which we have seen that is having both this Cox proportional as well as KM. Live table is there, but again, then all the 3, if it is there, then you can. Like if you want to publish a paper where you want to highlight the analytical aspect, then you can perform all 3. Right, because like there are many times our paper is very short and maybe there are not more tables. It's a short article or you want to highlight the analytical part of it, then maybe you can perform all 3. But you will say generally it is performed on the, RCT and prospective where a lot of tables are already there. So usually I have seen they only give this, even the adjusted hazard and the KM curve, not even the table which we have that cumulative survival. No one gives this table. Only this cumulative hazard, this hazard ratio But if you are interested in specific time intervals, if your research question is pertaining to that particular time interval, then again, definitely you can do that.
Okay, ma'am. Thank you.
But I have seen less article on life table, especially most of the article is on Cox proportional hazard, and KM is only just to see compare the curves. Because that is adjusted. In KM, you can only take one factor. If you want something adjusted, because there will be a lot of confounders also. So how you will, like we do for the linear, if you are only giving linear regression as a one outcome variable and one dependent variable, the validity will be less. So you have to do the adjusted one. You have to put a lot of other variables which you think that may act as a confounder or as a bias. So for that, I think it's better that you perform this Cox proportional, which we'll learn day after tomorrow. And give this KM curve also as a graph and that table. And in that case, you will see that JAMOVI gives good output for this Cox proportional. So are we all back in the main room, Arun?
All back.
Okay.
Ma'am, is there any option in JAMOVI to
Yes, ma'am.
change the axis name?
Change axis? No. We have written to Jonathan that there is some problem, and with that month also, which one participant was asking, that by default it takes it as a month because it doesn't give you the days. It will take time in bracket months. So maybe there's no option to change. It's in the image form. If you copy, it doesn't give you any other form. Like if you go to the SPSS, it gives you many forms. Like if you go to this SPSS, and if you want to like see copy this thing image, so it again gives you like copy special. So it gives you these options: image, Excel image, rich, plain text, and etc. But that doesn't give. Okay, it plainly takes it as an image. So we have tried this also. So you, in that case, what you can do, like maybe you can I don't know how to hide that and how to edit that. Maybe you can edit it, but that's difficult, editing it.
Ma'am, we just have discussed about the results are different in SPSS as well as in JAMOVI. Ma'am, while writing the manuscripts, in each results, we have to put in bracket that which software is used.
Which what is used?
Which software is used? That is
No. Don't do that. Then the reviewer and author, they will be confused. Only write in the statistical analysis that you have used both. No need to specify while you are giving the table and graph. You only make your table. No need to specify that this result you have taken from SPSS, this you have taken from that. So I was telling you that you can use both, according to your convenience. But when you are making a compiled result, no need to mention separately that whether you are giving this, because many times we do it using many this thing. Okay.
Okay, ma'am.
Any other query? If not, then we may end the session today, and then we'll meet again day after tomorrow. Okay, so Akanksha,
Yes, ma'am.
so kindly end the meeting.
Yes.
You have the Hindi font. You have. This will come for you.
Sir, how to end the meeting?